focus of this lecture will be on Huckel molecular orbital theory. This is a form of MO theory, a particular form that still adheres to, of course, the linear combination of atomic orbitals to form molecular orbitals, or LCAO-MO approximation, but it is a qualitative to semi-quantitative form of the theory that we can apply using very simple, relatively simple, sort of back-of-the-envelope types of calculations to describe the electronic structure of often relatively complex molecules, polyatomic molecules. To start out, our example is going to be ethylene, C2H4, for which we are very familiar with the Lewis diagram. Looks like that. For our purposes, I'm going to label the two carbons. I'm going to label them A and B, because we need to be able to distinguish between the two in terms of the construction of the molecular orbital. Now, there are a lot of electrons in this. Each carbon brings in 6 electrons. That's 12 plus 4 for the hydrogen, so we're up to 16 total electrons. But I'm not really interested in most of what those electrons are doing. I'm obviously not interested in what the core electrons on the carbons are doing, because they don't really have to do with, say, the bonding and reactivity of this molecule. Furthermore, as we have studied in valence bond theory, I can identify hybrid orbitals on the two carbons associated with the sigma bonds. Remember, in this carbon-carbon double bond, there is a sigma component, and then there's a pi component. The sigma component arises from the involvement of an sp2 hybrid orbital on carbon A overlapping end-to-end, that's why it's a sigma bond, end-to-end with another sp2 hybrid orbital on the carbon B. The remaining sp2 hybrid orbitals on each of carbons A and B are involved in the bonds with the hydrogens. But again, most of the chemistry, at least the initially interesting chemistry of ethylene, is not associated with those very, very strong sigma bonds. Instead, it's associated with the pi component of the double bond. And the pi component, as you can understand from our discussion of molecular orbitals for homonuclear diatomic molecules or heteronuclear, or our discussion of aspects of valence bond theory, the pi component here involves the remaining p-type orbitals that are out of the plane. And I'm going to choose the plane of the molecule arbitrarily to be the xy plane, which means that the z-axis is coming out of the plane of the board, which means that those pz-type orbitals on carbons A and B that are involved in that side-to-side overlap have a lobe out in front of the board and then behind the board, right? So there's side-to-side overlap between those two. I want to use Huckel MO theory to focus specifically on those two pz-type orbitals and their side-to-side or pi-type interaction. So in the spirit of LCAO-MO theory, I'm going to write that pi-type MO, psi sub pi we'll call it, as a linear combination of the psi 2pz orbital on A plus the psi 2pz orbital on B. And I have yet to determine what the coefficients are. Now, remember, the Schrodinger equation has the Hamiltonian as input and the wave function and the energy as output. This will be the structure, approximate structure of my wave function. Again, only describing the two pi-type electrons in the pi component of that double bond. Okay? So I need a Schrodinger equation. Now, in the Schrodinger equation that we're going to construct, we're only going to be dealing with it in a qualitative or formal sense. We're not going to actually build a Hamiltonian that we have to go through lots and lots of detailed integrals. The integrals that we will encounter, we're only going to evaluate in a very formal and qualitative way. You'll see what I mean. So here's my wave function, my approximate wave function. If I write down a Schrodinger equation for this, h psi pi is equal to e psi pi. That gets me started. And again, psi pi is just this linear combination of two pz orbitals on carbons A and B. Focusing again, this is only a Hamiltonian appropriate for those two pi-type electrons, one from each of carbon atoms A and B. Now what I'm going to do is I'm going to insert the form of this wave function on both the left and the right and expand. So what do I find? I find h times c sub a psi 2pza plus h c sub b psi 2pzb, that's the left-hand side, is equal to e times c sub a psi 2pza plus e c sub b psi 2pzb. This looks like it's getting much worse. Just hang on. Now what I'm going to do is think about for a moment, what's the input to my problem and the output? I already said that the Hamiltonian is part of the input, but I know other things here. I know that this is a 2pz hydrogen-like orbital centered on carbon A, right? So sticking out of the plane or going back behind the plane of the board, right? Lobes front and back. So I know what psi 2pza is. It's a known function. I'm not going to write out explicitly here, but just we agree that this is a known function. Similarly, the 2pz orbital on B is a known function. So if I look at this equation, supposedly I know my Hamiltonian, and I know my wave function components, called basis functions sometimes. What I don't know is the energy or my coefficients Ca and Cb. But remembering our discussion of homonuclear diatomics, since Ca and Cb, that is carbon A and B, are identical, the coefficients A and B, and it's unfortunately I've used C for both of those, the coefficients A and B should be equal in magnitude, okay? So again, because of the symmetry of the system, these coefficients should be the same. Now how am I going to find them? One way to do this would be to multiply this equation through on the left by psi pza. I'm going to multiply the whole equation on the left side by psi pza. I have to keep it to the left of the Hamiltonian because remember the Hamiltonian is doing things to the wave function when it's right. It's taking derivatives of it, for example, so I can't just move it in and out. But the coefficients and the energies, those are just numbers, so they can be moved out all I want. After I've multiplied this whole equation on the left by the 2pz orbital on A, I'm going to integrate all four terms, right? Formally, at least, integrate all four terms. So let's write that down, multiplying on the left by psi 2pza, and then integrating over all space. Since it's all space and I'm not defining a coordinate system, I will do something we've done before, which is define the differential volume element as d tau. Watch. First term, I keep the c sub a out front, and I'm integrating psi 2pza, that's multiplying it on the left, then my Hamiltonian, then psi 2pza. That's the first term, multiplied on the left by psi 2pza and integrated over all space, and I need d tau for my placeholder differential volume on it. Again, we're not really going to do this integral, right? We're going to assume it has some value that we're interested in later. Continuing through the remaining terms, I have a coefficient c sub b out front. Then the integral of psi 2pza, Hamiltonian, psi 2pzb, d tau. There's my second term. Continuing on, the third term, both e and c sub a are constants, so they can come out front. And the integral is just psi 2pza, psi 2pza d tau. And the final integral, ec sub b, integral psi 2pza, psi 2pzb d tau. Now this looks bad, right? I've got four ugly integrals that I've got to do. But again, I don't really need to do the integrals except symbolically. I don't need to actually work through a lot of detailed calculus because I'm going to make some simplifications. First, notation. This kind of an integral in which I have the Hamiltonian sandwiched between two wave functions, two pz functions in this case, both on the same carbon atom, A, I'm going to call that H sub A, just to simplify the notation. But remember, that's an integral, H sub A. If these were both centered on carbon atom B, this would be H sub B. Okay? Here's another one with the Hamiltonian sandwiched between two functions. This one's centered on A, this one's centered on B. What do you know? I'm going to call that HAB. If the A and B were reversed, then B and A will be reversed here in my notation. Okay? Energy and coefficients stay the same. This one doesn't have the Hamiltonian in it, but this one still gets a label. This one we refer to as S. And because both centers are A, that is going to be SAA. Here's another one, the same type of integral with A and B, however, and I'm going to call that SAB. And just as I saw for the Hamiltonians over here, if this is B and B, then that becomes SBB. If this is B and A, that's SBA. This is just to simplify our notation. Okay, so now I'm going to make some approximations. Oh, before I do that, let me write down this with the new notation. So I've got C sub A, HAA, plus C sub B, HAB, is equal to E C sub A, SAA, plus E C sub B, SAB. Now that looks a lot simpler at this point. Again, what do I know and what do I not know? Presumably, I know how to calculate these integrals because they consist of the functions that I already know and the Hamiltonian. But what I don't know are the coefficients CA and CB and the energy, input versus output. Now I arrived at this equation by starting from this Schrodinger equation, multiplying on the left by psi 2pz A, and then integrating over all space. What if instead I'd multiplied on the left by psi 2pz B? Then the equation changes only a little. Here I would have a psi 2pz B HA. That would become C sub A HBA for that term. Here I would have C sub B times the integral over the Hamiltonian sandwich between psi 2pz B and psi 2pz B. That would look like C sub B HBB. On the right-hand side now, I would have BA here, SBA for that term. So E C sub A SBA. And for the last term, I would have E C sub B SBB. These are my two simultaneous equations. They have to hold in order to determine the energy and the two coefficients. Now, here's where, so far, my approximations have only been that I'm only taking the linear combination of two 2pz type orbitals. Everything else has flown through with no other approximations. Now here come my Huckel approximations for Huckel MO theory. First, integrals like HAA and HBB that involve basis functions of the same carbon atom, right? So a 2pz both on carbon A or both on carbon B. So HAA, this is the same as HBB because of the symmetry of the system. Carbon atoms A and B are identical. This is going to be something I call a quantity alpha. This is called a Coulomb integral. The value of alpha I'm not really going to be concerned about, okay? One could technically calculate it, but that's not of interest for our purposes, which is to get a qualitative or maybe semi-quantitative understanding of the electronic structure of this molecule. Okay, those are HAA and HBB. What about HAB and HBA? HAB, which has to be equal to HBA, we call this beta, so our consistent notation there. And this is called a resonance integral. It is a negative number. It may be shown that, which always means in my classes, if I say it may be shown that, that means I'm not going to show it. I'm just asking you to trust me. Beta is a negative number. In fact, beta is approximately negative 2.4 electron volts for systems involving carbon atoms like this. And that is about negative 230 kilojoules per mole. So those are good numbers to remember. So it gives you a magnitude of these quantities. So I'm going to call HAA and HBB alpha, my Coulomb integrals, HAB and HBA, my resonance integrals beta. Well, what about these S's? So SAA and SBB, I'm going to call those 1. Those are our favorite integrals, right? Where the integral turns out to either be 1 or 0. Meanwhile, SAB and SBA, I'm going to take those to be 0. These are assumptions on my part. They don't necessarily have to hold, but they make the math simpler. These types of S integrals are called overlap integrals. That's wonderful because These three components simplify the look of these equations significantly. Now I'm going to replace all of my symbols in here with alpha, beta, 1, and 0 where appropriate. And what do I find? Coming from here up to here. I find C sub A times alpha plus C sub B times beta is equal to EC sub A. And that's it, because SAA is 1 and SAB is 0, so the rest of that term's gone. That's my first equation. Looks a lot better. The second equation now switches the alpha and beta. I get C sub A beta plus C sub B alpha equals, in this case, SBA is gone, and here SBB is 1, so that becomes EC sub B. Those equations look much more manageable. We're assuming that I know what alpha and beta are, and now I only have to figure out the two coefficients, CA and CB, and the energies. That's it. Okay. What I'm going to do next is I'm going to collect like terms. I have a C sub A here and here. Move the E C sub A over and collect it with the other term involving alpha. What do I get? Alpha minus E C sub A plus beta C sub B equals 0. Switch the ordering on these to keep the coefficients to the right. Now I'm going to do the same thing with the C sub B term, and what do I find? Beta C sub A plus alpha minus E C sub B equals 0. These are now my two working equations, where I've collected like terms and I have only zeros on the right. Now, I'm going to switch notation again. I'm going to switch this from explicit equations to a matrix notation. And for those, if you're not familiar with matrix equations, Google is your friend. You can find a simple tutorial on this, or you can take a look at justifications in your book. This one's only going to be a 2x2 matrix where I collect the C coefficients in a vector and the coefficients in front of the C coefficients in a matrix. So what do I find? I get alpha minus E, that's the first coefficient, and then beta. So there's my first row of my matrix. The next one has beta in place, and then alpha minus E. That's the vector of coefficients. And then, the matrix of coefficients, the vector of the C coefficients, is just simple. And this equals a vector of zeros on the right. It is 2x2 because I have two equations and two coefficients. Now, going backwards from the matrix notation to the equation, you multiply the first row times the column to give the first row on the other side. So I get alpha minus E times C sub A, that's that term, plus beta times C sub B is that term, equals 0. That's my first equation. The second row gives me the second equation. Beta times C sub A, that's that term, plus alpha minus E times C sub B equals 0. So this notation encompasses both of those equations in one single matrix equation. I do this because there's a special property of matrices that says when I have a matrix like this that is non-zero times some set of coefficients as a vector equals a 0 vector like this one here, that can happen if what is called the determinant of this matrix, the determinant of the matrix is 0. What is a determinant? Well, a determinant can be thought of very simply. It's just a number in the end associated with all the components of the matrix. For a simple 2x2 matrix, say it's got components A, B, C, and D, the determinant of a 2x2 is simply the product of the diagonal elements minus the product of the anti-diagonal elements. So that determinant is A times D minus B times C. Analogy from here to here, this is quite easy. I can simply take the product of the diagonal elements, which is alpha minus E squared, minus the product of the beta elements, so the anti-diagonal elements, that's beta squared, and set the whole thing equal to 0. Now I have something that is strictly in terms of my Coulomb and resonance integrals, which I assume I know, and energy, which is what I'm looking for. This is a quadratic equation in energy, which you can then plug into the quadratic formula or be very clever about factorizing it, and you will find that E is equal to either alpha plus beta or alpha minus beta. It's a quadratic function, therefore you're going to have two solutions to it at most. Which one is lower in energy? Well, they both have alpha, so it all depends on beta. But I told you that beta was a negative number. Therefore, the lower energy is alpha plus beta. The higher energy is alpha minus beta. So now that I know my energies, I'm in a position to draw the same kind of energy schematic diagram that I did for some of the other systems when we talked about basic MO theory. Let's come back over to this side and do exactly that. We'll draw, I'll keep our approximations here on the board for now. But I will draw an energy level diagram. This one doesn't have to be very large because there's only two energies. As I said, the lower energy is alpha plus beta. So alpha plus beta. And the higher energy is alpha minus beta. How many electrons am I dealing with here? Don't forget, don't get lost in the math. We are only dealing with the two pi type electrons, one from each carbon associated with the double bond. Since there are only two electrons, using the building up principle, I can put both of them in the lower energy orbital. Now, there is my electronic configuration for this. These are both pi type orbitals, right? I haven't said anything yet about what the coefficients look like though, right? The coefficients sort of disappeared at this step because I used the determinant to figure out the energy only. I still need the coefficients. I'm not going to go through an explicit solution to those because I actually need another equation to determine them exactly, the normalization equation for those of you who are interested. But the lower energy orbital consists of psi pi 1, we'll call it, looks like 1 over square root of 2 psi 2 pz a plus psi 2 pz b. That, because of the plus combination, means that I've got a bonding, side-to-side bonding overlap between the two pz orbitals centered on each of those carbons. Meanwhile, the anti-bonding orbital here, psi pi 2, is also a 1 over root 2 out front, but it is psi 2 pz a minus psi 2 pz b. That's the anti-bonding orbital because the signs flip on the second term, causing destructive interference in the bonding region. That's why this is an anti-bonding orbital, and the first one is a bonding orbital. Now, in the case of Huckel MO theory, it is common to calculate what's called the pi electron energy associated with this molecule. And we're treating the two electrons, apart from obeying the Pauli exclusion principle as we have, we treat the two electrons as independent of each other. This electron with the alpha spin has an energy of alpha plus beta because it's in an alpha plus beta orbital. The one with the beta spin down, also has an alpha plus beta energy, and the total pi electron energy then is just 2 times alpha plus beta because there are two electrons. Let's move on to a somewhat more complicated system, but certainly I think more interesting and instructional system. In this case, I was just trying to describe the pi bonding orbitals and anti-bonding orbital, of ethylene, the pi electron system in ethylene. It's relatively simple, and it has a lot in common with the homonuclear diatomic problem that we've already discussed. Let's go to a more complicated system. Let's now take a system with 2 double bonds. Let's go to butadiene. I'm going to leave a little bit on the board just for reference sake. I'm going to draw this out in Lewis form explicitly. And as I told my class before, you can tell I'm not an organic chemist because I will draw in all the hydrogens. So in Huckel MO theory, again, I'm trying to describe only the pi electrons associated with this interesting conjugated molecule. First thing I need to do, just as I did before, is label the atoms, my carbon atoms, so I can keep up with which center is which. Analogous to what I did for ethylene, I'm going to label these A, B, C, and D. 4 of them, A, B, C, and D. And the total number of electrons I'm trying to describe here is 4, because there's one pi electron associated with each carbon atom. Now, when we built ethylene, we explicitly wrote out our wave function, approximate LCAO-MO wave function. We stuck it into a Schrodinger equation associated with the pi electrons only, and then we multiplied on one side by one of our two carbon PZ type functions, and then did integrals. And then we simplified our notation as such, and then filled in a determinant like this. I want to use that same structure, but I'm going to try to skip steps because the concepts are exactly the same. There's just more algebra involved. So let's avoid algebra whenever we can. So what happened? On the diagonal of the determinant expression for ethylene, I had alpha minus E. Alpha was the Coulomb integral arising from a single carbon center. There I only had A and B, but here you can predict I'm going to have 4 of those Coulomb integrals, one for carbon A, one for B, one for C, and one for D. Don't forget, the functions that we're using on those carbon atoms are PZ type orbitals that are perpendicular to the plane of the molecule, because I'm assuming that the molecule is in the XY plane. Okay? So that's, again, it's the same kinds of functions that we use for ethylene, because we're only describing those PZ pi type interactions. But since I have 4 of these, I'm going to have 4 types of Coulomb integrals, or 4 alphas. The ethylene determinant was 2 by 2 because I only had 2 carbons. Now for the butadiene determinant, it must be 4 by 4 to account for the whole system. Okay, so I'm going to have a Coulomb integral, alpha, on the diagonal, because just on the diagonal here, alpha minus E has to appear on the diagonal in all 4 rows of my full determinant. Let's write those down for now. So this is the determinant that I ultimately have to solve. I'm going to label the rows A, B, C, and D for clarity with these. And of course the columns will also be A, B, C, and D. Okay? And the whole determinant in the end is going to be equal to 0. The diagonals then correspond to a Coulomb integral for each center, in this case AA, minus the corresponding energy, just as we saw in ethylene. So on the diagonal AA, I get alpha minus E. On the BB term, another alpha minus E. For the CC term, alpha minus E. And DD, alpha minus E. So those diagonal terms don't change for these compounds that only involve carbon atoms, because there's only one type of Coulomb integral. Now let's talk about the off-diagonal elements. In ethylene, I had an AB and a BA. Those correspond to an integral in the AB or BA components, the off-diagonal components that you see here. And they were resonance integrals, right? So they involved, in the case of ethylene, a Hamiltonian sandwiched between a PZ orbital on A and a PZ orbital on B. And the key point being that those 2 carbon atoms were adjacent to each other. They're side by side here. What else is adjacent? Well, B and C are adjacent, and C and D are adjacent in butadiene. However, A and C aren't adjacent to each other, right? There's a carbon in between. A and D are not adjacent, and similarly B and D are not adjacent. So here comes Huckel Approximation. So this is Huckel Approximation number 2. This was Huckel Approximation number 1, that the overlaps are either 1s or 0s. Huckel Approximation number 2 is that beta ij, where I and j are A, B, C, or D. This is equal to just beta if and only if I and j are adjacent to each other. Side by side, right? If I've drawn a bond in my Lewis structure, I'm going to call that adjacent, no matter whether it's a single or double bond. But beta ij is going to be 0 otherwise. That helps us a lot here, right? Because that means that for any combinations I and j, meaning A, B, C, or D, in which the 2 indices are not adjacent to each other, I'm going to put a 0 in the matrix. So how about the AB position? Well, that corresponds to A and B, which are adjacent, so I put a beta resonance integral there. Similarly for BA, right? It's the same thing because this matrix has to be symmetric. How about AC, this position? Well, A and C are not adjacent to each other, so by the second Huckel approximation, I put in a 0. Similarly, CA also has to be 0. AD. A and D are very much not adjacent to each other, therefore I get zeros in the AD and DA positions. For the BC position and CB, they are adjacent. You get a beta. CB, beta. However, BD, B and D are not adjacent. You get a 0. And the last two positions correspond to CD and DC, which they are adjacent. A lot of new zeros come up in this thing. All right. Now we've constructed the Huckel determinant. This is also called a ckel determinant. Which is the language that is used in the mathematics or the linear algebra for this. But if you construct the determinant for this 4x4 matrix and then solve for the energy, this is not a simple thing by any means because you get a quartic equation in E, then you get a set of energies, which I will draw in the same kind of schematic diagram that we did before. So these are the energy levels of butadiene, and because the matrix is 4x4, the resulting equation in E is quartic, which means there are 4 solutions, right? 4 distinct solutions for this. The lowest energy solution corresponds to alpha plus 1.618 beta. I'm not making it up, right? So if you actually go through and solve these things explicitly, if mathematics is your favorite, use that. That's a good one to try. One of the equations comes out to be alpha plus 1.618 beta. A little bit higher than that is the next one. That's alpha plus 0.618 beta. And because beta is a negative number, 1.68 beta is lower than 0.6818 beta. And then I get 2 more, alpha minus 0.618 beta and alpha minus 1.618 beta. 4 energies associated with this 4x4 determinant because I have 4 pi electrons in my butadiene system. But those 4 pi electrons now fill up these orbitals using the same building up principle from lowest to highest. I can therefore put 2 electrons in alpha plus 1.618 and 2 electrons in alpha plus 0.618 beta, and that gives me my total energy of the system, the ground state I should say, for a pi electron energy of 4 alpha plus 2 times 1.618 and 2 times 0.618 beta. So that's that total pi electron energy. That is also interesting because we could also ask the question, is this lower or higher in energy than the energy of 2 separated ethylene systems? We just talked about what the pi electron energy was for ethylene. So for 2 pi electrons in ethylene, so let's say 2 instead, 2 separated C2H4 molecules. The pi electron energy for that is going to be 2 times 2 alpha plus 2 beta. That's the pi electron energy for one ethylene molecule that we just determined. So therefore, this is 4 alpha plus 4 beta, right? So now, this number here comes out to, if I complete this, that is 4 alpha plus 4.472 beta. So the pi electron energy here involves additional contributions from this negative resonance integral relative to 2 separated betas. So the difference between those two is what we call the delocalization energy, E delocalization, which is the difference between the pi energy of your true system, butadiene in this case, according to Huckel theory, and the pi electron energy for n C2H4 units. In this case, 2 C2H4 units because there are 2 double bonds. Now, I just said something that's a bit problematic. I said there are two double bonds. We have to be very careful about that. Because are there two double bonds? I haven't shown you what the orbitals look like yet. That's next. But comparing to two ethylenes, because that matches the total number of carbons, I can see that there is an additional stabilization here of 0.472 beta. That puts it lower in energy than two isolated C2H4s. That means that butadiene has some additional pi stabilization or delocalization energy relative to the separated fragments. That's a very important concept. But what do these orbitals look like? Okay, when we draw it like this, typically, I've shown you two localized pi double bonds. But that's not really a correct statement. Right? According to Huckel theory, the orbitals look a little bit different than this. In particular, I'm going to get 4 MOs, one corresponding to each energy. I'm going to draw them low to high here, moving up in energy. And I'm going to call the first one psi 1. And this turns out to have coefficients C, I'll call it Ca, psi 2pz on A, plus Cb, psi 2pz on B, plus Cb, psi 2pz on C, let me draw that a little bit better, on C, plus Ca, psi 2pz on D. Now let's take a look at that and be very careful. This structure of coefficients, where the inner two carbons have the same coefficient and the outer two carbons have the same coefficient, reflects the symmetry of this molecule. Clearly, A and D look identical. They're both attached to two hydrogens on the outside and inwardly with a double bond to carbons B and C. They're equivalent to each other by the symmetry of the molecule. If I rotated the molecule clockwise or counterclockwise by 180 degrees, it would look exactly the same. That's why wave function A and function D have the same coefficient. Functions B and C have the same coefficient, all with the same signs. These coefficients, C sub A, turns out to have a value of 0.37. Okay? I could give you more significant figures, but we'll just stick with 2. Okay? And CB has a coefficient of 0.60. So CB is bigger than CA. Let's keep that in mind. So if I were to draw this in terms of the PZ type orbitals, so psi 1, I'm going to draw it out here, at least approximately, for carbon A, carbon B, carbon C, and carbon D. The PZ orbitals on the inner carbons are bigger than those on the outer because they have a bigger coefficient. So if I draw those PZ orbitals, that's not too bad. And they have the same sign. Those on the outer carbons are smaller, so I'll draw them smaller because they have smaller coefficients and they have the same sign. That corresponds schematically to the lowest energy orbital. And to make sure that you understand what I've drawn here, these are PZ type orbitals. So I'm looking in the plane of the molecule. It's as though I took this molecule, rotated it out of the plane, and now I'm looking in the plane at those PZ orbitals sticking up above and below the plane of my butadiene molecule. That's only one. Let's take a look at the next one. The next one here switches the positions of coefficients A and B and changes the sign. So psi 2 is going to have C sub B psi 2pz on A plus C sub A psi 2pz on B minus C sub A psi 2pz on C minus C sub B psi 2pz on D. Again, I have not proven these equations to you. They come out naturally from the solution of the secular determinant and then the subsequent determination of the numerical values of the coefficients. We're skipping those steps here, and I'm just trying to give you the final results. What does this orbital look like? Let's plot it in the same frame. Now I've got A, B, C, and D, so I'm looking in the plane of the molecule again. Now the big ones are on the inside, on the outside, so I get lobe. I did that wrong. Let me try this again. stick with me. A, B, C, D. I want large ones out here, and I want small ones on the inside. Because again, the smaller coefficients are on the inside, the bigger coefficients are on the outside. But what about the signs? The first two have the same sign, but the next two have their signs flipped. Fascinating. This is important because now, since I go from a positive sign to a negative sign as I go left to right across the molecule this way, that implies that I must have a node right in the middle. This is typical. If you think back to what we saw for the particle in a box, the bottom, the ground state wave function had no node. The second wave function, the first excited state wave function, had one node. You can guess what's going to happen to orbitals 3 and 4. Let's take those. Psi 3. Psi 3 now keeps the positions of Ca and Cb, but moves the signs in this case, okay? So I get Cb psi 2pza minus Ca psi 2pzb minus Ca psi 2pzc plus Cb psi 2pzd. Look at the pattern of the coefficients. How does this work out? Psi 3 now looks like this. There's A, B, C, and D. The big lobes are still on the outside because that's Cb. The small lobes are still on the inside. But now there's a sign change between A and B, no sign change between B and C, and then a sign change between C and D. Where are the nodes? Now I have a node here and here because traveling left to right, positive, negative, positive. 2 sign changes, 2 nodes. You can guess what's going to happen to the fourth MO. I'll give myself a little more room. And again, there's a correspondence in energies here. The fourth MO, psi 4, is going to switch the positions of the coefficients back to what they were to begin with, but now I'm going to alternate signs. Like so. A, B, B, A for the coefficients, but plus, minus for the signs, which means that psi 4 looks like this. A, B, C, D, small lobes on the outside, big lobes on the inside because of the magnitudes of the coefficients. And if this one starts out with that sign, I have to switch them back and forth for the other 3 terms. So now I get a node in between each p-type orbital, moving left to right across the molecule. And again, that, number 4, corresponds to the highest. Think about this in terms of bonding and anti-bonding character that we examined before. Bonding character meant I had a constructive interference in the side-to-side overlap of the pi-type orbitals. That's exactly what I had right here in psi 1, my lowest energy orbital. I get this lovely constructive interference all the way across because I get side-to-side overlap of lobes with the same sign. So this is clearly a bonding type orbital. But how about this one? Do you call this bonding or anti-bonding? Well, it's a little of both, right? Because here I've got positive constructive overlap between these 2 p components because constructive interference, the signs are on the same side in the side-to-side overlap. I also get constructive interference on these latter 2, right? 3 and 4, or C and D. Similar kind of overlap between the same signs on the lobes. But in between, now I have anti-bonding character because I've got destructive interference in between, and that's what gives rise to the node. Well, let's look at psi 3. Again, a little of both. There's bonding character between carbons B and C, but anti-bonding character everywhere else. And for psi 4, there's nothing but anti-bonding character. So we don't normally label these bonding and anti-bonding. We really just label them pi 1, pi 2, pi 3, and pi 4 because they have, at least starting from everything except the bottom one, they all have a little bit of anti-bonding character. Let me make one more point about this. And that is to repeat the comparison to the particle in a box. When we drew the particle in a box wave functions, For n equals 1, if you remember, the length of the box was L, 0 to L. For n equals 1, the wave function looked like a half period of sine, which is very much like this. When I went up to n equals 2, then the wave function looked like a full period of sine, which is very much like this, if I could draw it better. Okay, full period of sine, same general shape. 3, and they should be getting further apart based on energy, but just bear with me. Now I get 1.5 periods of sine, which is exactly what I get here, though it's not as beautifully symmetric as that would be. And for the fourth one then, I'm going to get 2 full periods of sine. But you see the analogy here. Numbers of nodes, 0, 1, 2, 3, 0, 1, 2, 3. This further justifies why we use the particle in a box model to great success to describe the pi electrons in benzene, right? We did extremely well describing what the lowest excitation energy was, but now Huckel theory gives us a more quantitative, or at least an alternative quantitative structure, because the excitation energy can be determined as the energy difference between the HOMO, or the highest occupied molecular orbital, and the LUMO, the lowest unoccupied molecular orbital. And if I know a value for beta, I can estimate what that is. So with various properties that we can extract from simple theories like Huckel MO theory, we can learn a lot about the internal structure, or at least the most significant points of internal structure, such as the pi electronic structure of molecules that are much more complicated. If we go on to longer polyenes, then we see that the secular determinant is going to get larger and larger with the number of carbons, and there reaches a point where we really can't do these things by hand. We have to use a computer to handle these things much more rapidly for us. When you get to other kinds of structures, especially cyclic structures, you should keep in mind the nature of the Huckel approximations. Take, for example, cyclobutadiene, right, which is just 4 carbons here. I'm not going to bother to draw in the double bonds. And see if you understand why. I'm not drawing in the double bonds because even though we would draw them in a Lewis structure like this for butadiene, not cyclo, but butadiene here, it's clear that that structure doesn't necessarily hold with what the quote-unquote reality of molecular orbital theory says. Where are the double bonds in that or that, right? So the way to think of it is really that things like single, double, and triple bonds don't actually exist. They're useful models, but they don't necessarily hold to a physically observable thing. Molecular orbital theory gives a slightly more sophisticated, nuanced picture of it, but these are also models. They don't exactly exist. So I'm not going to draw in double bonds for cyclobutadiene here. Instead, I'm going to simply point out that I've got my 4 carbons. There are 4 pi electrons. So I would have a 4x4 determinant similar to what I had for butadiene. However, in this case, the positions of what's adjacent and what's not are now different. Let's label A, B, C, and D as we did before. Let's look at our 4x4 determinant with the rows and columns labeled A, B, C, and D as before. On the diagonal, yet again, I have alpha minus E for each entry. Alpha minus E, alpha minus E, alpha minus E, and alpha minus E. But what's interesting is what happens on the diagonal. Between A and B, I get resonance integrals, just as I did for butadiene. Between B and C, I get resonance integrals, just as before, and between C and D, resonance integrals. So this part so far is exactly identical to butadiene. Furthermore, A and C are not adjacent. Therefore, I get zeros in the AC and CA positions. B and D are not adjacent, so therefore I get zeros in the DB and BD positions. But here's where it's different. A and D are now adjacent to each other because it's a cyclic structure. So whereas the DA and AD components in butadiene were 0, in cyclobutadiene, I get a resonance integral. That will change the resulting energy levels that I get. There will still be 4, but they're not the same as these. And so that gives us different insight into the unique electronic structure of this molecule. So that's just a little bit of a caveat when it comes to building more complex structures. Benzene is a wonderful structure that has a similar general structure to this. If we build the symmetry of the molecules into this, then we can make these much more easily solved within the context of the point group symmetry of the compounds. So that's our coverage of Huckel molecular orbital theory, and I hope that you found it useful.